When an aircraft snaps into a sharp bank, it immediately tests the physical limits of its lateral control. The forces at play dictate whether the plane holds its trajectory or spirals out of control. To understand these forces, we have to isolate two specific aerodynamic coordinate systems: the YZ roll plane, where the aircraft banks, and the XY yaw plane, where the aircraft turns left or right. The primary tool designers use to manage motion between these planes is the dihedral angle, denoted by the Greek letter gamma. This is the specific upward angle the wing plane makes with the horizontal axis when viewed directly from the front. Engineers implement this angle to provide roll stability and to dampen dynamic modes like Dutch roll. Dutch roll is a coupled oscillation where an aircraft simultaneously rolls and yaws, creating a continuous figure-8 motion. The mathematical representation of this stability is the derivative Cl beta, commonly called the dihedral effect. Cl beta measures how much rolling moment is generated per degree of sideslip. Yet this introduces a kinematic paradox. A banked aircraft attitude through a pure roll keeps the aircraft motion entirely within its plane of symmetry. A pure roll remains perfectly symmetrical to the incoming relative wind, providing zero inherent restoring moment. An aircraft cannot mechanically fix a roll using only the roll axis. In this front orthographic view of the wing geometry, we isolate the upward lift vector, Ln, normal to the surface. The geometric dihedral tilts this force inboard, projecting a new vertical vector, Ln cosine gamma. The static lift equation expands to Ln equals QSCL alpha alpha cosine gamma. This proves that dihedral mathematically reduces the effective angle of attack by a factor of cosine gamma. For typical commercial and general aviation aircraft, these dihedral angles are highly constrained, usually ranging from only 4 to 7 degrees. At 4 to 7 degrees, the squared cosine gamma term factor is 0.995 to 0.985. Because this raw loss of static lift is mechanically negligible, the geometric dihedral does not exact a heavy penalty in level flight. Its true aerodynamic power only activates during dynamic lateral motion. Shifting perspective to the rear of the aircraft, we observe the initiation of a positive roll angle, denoted as phi, where the right wing drops. As this happens, a downward weight vector originates from the center of gravity. As the aircraft banks, the primary lift vector tilts. This breaks vertical equilibrium, allowing the aircraft's weight to pull the airframe laterally downward toward the dropped wing. This lateral slide triggers a new directional velocity component, the sideslip velocity, v. Meanwhile, the aircraft maintains its primary forward freestream velocity vector, u, moving straight along the x-axis. The interaction of these vectors defines the sideslip angle, beta. Mathematically, beta is the inverse tangent of the lateral sideslip velocity divided by forward velocity. This creates an absolute aerodynamic rule. A positive angle of roll mathematically guarantees the generation of a positive sideslip angle. Roll stability is entirely a byproduct of directional dynamics. The aircraft must physically slide sideways through the air before it can generate the forces required to save itself from rolling. This visualization shows relative wind striking from an offset angle, U tan beta. On the dropped wing, side flow strikes the underside, increasing its angle of attack and triggering a lift surge. Conversely, flow over the raised wing decreases its angle of attack, reducing lift. This severe asymmetrical lift creates a powerful mechanical torque across the airframe. This is the restoring rolling moment, pulling the aircraft back toward level flight. A common misconception is that roll stability systems fight the roll angle itself. They do not. The strict stability criteria dictate that the restoring moment coefficient, Cl, must be plotted against the sideslip angle, beta. The roll angle, phi, is mathematically irrelevant to the actual restoring force. For stability, the sign convention requires Cl beta to be negative. An increase in the sideslip angle must directly yield a counteracting rolling moment. Dihedral is simply a geometric tool. It exists to capture the sideslip wind and convert it into a restorative lever against the roll. Geometric dihedral is only a baseline. The total effective dihedral of an aircraft is heavily manipulated by secondary airframe configuration choices. This diagram compares vertical wing placement, which acts as a major contributor to lateral stability. As air flows around the circular fuselage during a slide slip, it creates a crossflow effect. On a low-wing design, this fuselage crossflow alters the relative airflow over the dropped wing, reducing its angle of attack. This creates a destabilizing effect that must be countered by increasing the upward dihedral angle. High-wing aircraft experience the exact opposite crossflow effect. The airflow gets pushed up into the dropped wing, granting these airframes highly pronounced inherent roll stability. In many designs, this inherent stability is actually too strong. It forces engineers to apply anhedral, a negative dihedral angle pointing downward, just to compensate. We can see this effect clearly demonstrated on the BAE RJ series aircraft and on the Harrier. Both utilize high-wing configurations, and both require an aggressive downward anhedral droop simply to remain maneuverable. Wing sweep back acts as the second major configuration variable that functions as a powerful, effective dihedral. This top-down view of a swept-wing aircraft in sideslip illustrates the aerodynamic geometry. The windward wing presents a reduced sweep angle to the incoming air. This drastically increases the normal component of the air velocity, generating a substantial lift increment. For highly swept military aircraft, this effect generates a rolling moment so powerful that it creates excessive roll stiffness, making the aircraft resistant to pilot inputs. To maintain the quick roll response required for combat or high-speed maneuvers, designers must intentionally cripple this naturally occurring stability. This photo of the Tu-104 taking off provides a textbook example. Even though it is a low-wing aircraft, it requires an anhedral droop purely because its extreme wing sweep generates too much lateral stiffness. Aircraft designers constantly balance opposing aerodynamic forces. They must weigh sweep, wing height, and dihedral against each other to achieve a specific target CLB beta. When a single dihedral angle is insufficient to balance these forces across complex flight envelopes, designers invent hybrid geometries. Notice the FMA IA-58 Pucará in this photo. It features a cranked dihedral, where the stability characteristics purposefully change along the span of the wing, outboard of the nacelles. This image of the McDonnell Douglas F-4 Phantom highlights a masterclass in brute force stability tuning. To fix severe stability issues discovered late in testing, engineers applied a cranked dihedral strictly to the outer wing panels. Roll stability is never as simple as tilting a wing upwards. It relies entirely on kinematic coupling, a strict mathematical process of capturing side slip data and translating it into a precisely engineered restorative force.